So we have here with us Professor Niloy Ganguly, Professor Santiago Segarra, Dr. Philip Chodrow, and yes, so we can start with maybe some opening remarks, and we have thought about some questions together with all the organizer of this workshop. And the question with whom we would like to kick off this discussion is general comments and remarks about interesting complex network structure you are currently working on or you have worked in the past, and what, according to you, are the exciting problems that require the use of this complex network structure, or which one are the problems that will require in the future the need of this complex structure. So if anyone that wants to start, feel free to break the ice and unmute yourself.
Sure, okay, let me start with that, and then here my colleagues can take over. So, yeah, so good complex network structure. So as kind of what's probably could be seen from a bit from my talk, in a lot of cases, we've been working with this trajectory prediction, where the simplicial, we were thinking in terms of simplicial complexes, and those would come from discretizations of some, let's say, some manifold in general. And in my view, part of the gain there comes in the fact that having these phases, or if you think of higher dimensions, maybe having volumes and stuff like that, allows you to encode these holes or obstacles. So in terms of trajectory prediction or trajectory design, this can be way more powerful than a graph. So let me try to iterate what I mean by that, right? Let's say that you start with some plane and you have some hole in the middle. You could still certainly discretize this plane with a hole just using a graph, and think of discretizing this with different finer levels, right? If the graph is very coarse, you actually don't really see that there's a hole in there. The graph cannot see that there's a hole because the coarseness of the discretization and the coarseness of the hole could be of a similar size, let's say. So you need to go into finer and finer graphs to actually have the graph kind of see the hole. Now, if you're given this additional level of freedom where you can patch faces, then you can tell that there's a hole in there without needing to go into super finer discretization. So this will allow you, it's probably good in terms of scalability, and good in terms of convergence to applying some learning technique into the actual continuous space that lies behind us. So, so in a lot of my things that we are doing, these complex structures actually, again, arise as some discretization modeling of something that might be continuous, and then you can use this as a better discretization tool than just graphs.
Okay, very, very interesting. I think it's a very new approach to discretize network object. So yeah, I'm sure somebody else has comment or wants to add something new.
Yeah, I'll jump in. Hi everyone, my name is Phil Chodrow. So I'm a proud substitute for Dr. Jamie Haddock, whom you heard from earlier. And in her talk, on which she and I collaborate with Dr. Nicole Eichmeyer as well, we do work on hypergraphs, and this has been a bit of a theme in some of my recent work. Where I find hypergraphs to be really nice tools is when we are considering set valued data. So hypergraphs are really natural representations for data in which each observation consists of a set of discrete objects, and in some sense I say model, but in another sense that's literally what they are. So the gap between the representation and the data structure there is very, very small. And one of the things that I think we've been grappling with in the network science community is, when does the hypergraph structure, so the existence of sets that are larger than size 2 in your data, when does actually tracking that kind of structure lead to something new and different, something that you couldn't have seen if you had only modeled pairwise interactions? And I think there's sometimes we see a lot of hype around, hypergraphs or simplicial complexes are the next big thing, higher order interactions all the way. And it's true that we have been learning more about what we can actually get from these structures that it's distinctive. It's also true that I see some scholars who are doing amazing work discovering, oh, actually, there's some things that we thought were very distinctive about these that actually we can also model with graphs. That's a really good thing to know. But we are seeing different models with distinctive dynamics, usually nonlinear dynamics on hypergraphs. From Professor Haddock's talk today, we see that there can be different kinds of answers in the fundamental limits of community detection problems when using explicitly hypergraph-based algorithms. So there's a lot of open questions around when are these the right or most advantageous data representation for the data that you have? When could you do just as well with a simpler structure? And what kinds of analytic and mathematical implications come from those modeling choices? Tons of stuff to do there, and it's an exciting place to be.
Sure. Should I go after it?
Yeah, sure. Go ahead.
So I have some small slides to go for. Yeah. Yeah. So as you see that my group is also called Complex Networks Research Group, and it has been there from 2005. And when I was thinking about this, I was thinking of various phases of complex network research, how things have evolved and how I have looked into this. So if we see the first phase, which is from 2000 to 2010, perhaps. So we have seen all sorts of evolution, growth models. Then percolation had been an important thing, and then there has been community formation, all sorts of various papers, various influential papers around these topics actually came around those times. And we had this complex systems sort of communities, I think communities around ECCS, and mainly driven by physicists who has driven this phase of research, what I have felt. And then I think during the phase 2, there has been some sort of divergence from physicists and computer scientists. I think the second phase, with the advent of online social network sort of things, a lot of data began to come. So the first phase was more model driven, how important models we can make. And the second phase was more data driven. It was more data science sort of things which came out with online social networks. And we saw communities around ICWSM, if you know that ICWSM become a big community that time, and people people also understood that time that it is not only the network, there are other things, other issues which needs to be also taken into consideration, like the data, the language, and people were doing all sorts of recommendation services, and later which like expert identification or AI for good. So this type of things was done on online social networks, where there were networks, but there were also other tools which were used like NLP. And I think then the third phase started at certain point where we begin to see again, there are marriage, means the concepts of networks are coming back with learning together. And I think that is what the topic is, how we are mixing learning, reasoning with old complex network sort of things. And so still now it is, I feel still in the learning phase, we are not using a lot of our classical complex networks tools, but it is still coming. GNN is there. It's not really, we cannot claim that it has come from complex networks, but we have seen a lot of learning-based algorithm around community formations, etc., etc. And these things are developing day after day. And I see a lot of papers in recent new RIPs or ICML are coming around this area. So this is how I see that the topic has evolved. And the nice thing is we are seeing a marriage of learning and complex networks in recent times. In this thing, I think I would just, maybe some of you may have listened to my talks, but one of my big research agenda is like considering molecules and generating molecules from some latent space like Z, where we generate the types of molecules, the edge type, etc. So it's not really a, so from complex network perspective, it's not as big as a complex network, but it has many properties of a complex networks, like it has motifs, etc. And one needs to generate it from a latent space. So this latent space is somehow learned through some encoding function. The other tasks which we are doing is like crystal graph structure pre-training. So there is a lot of, so when we are talking about crystal, that also gets converted, can be converted into a graph structure. And this graph structure has rich structural as well as chemical informations. And this can be used as a typical self-training. So we are now using graphs as a self-training mechanism, and then developing a lot of knowledge about crystals through self-training and using it for downstream tasks. So these are some of the areas on which I am presently working. So I just again going back and forth from my work and the research questions. So what I've always thought that what was the difference between original complex network research and present scenarios. So if we see the, since I am a little bit older, so say we had initially this model driven things, and that many times became data driven. And it is not only about the change in the modeling structure, but also questions asked are different. Like if you remember, the opinion dynamics has been also a classical complex networks question. But what was initially asked, that some question asked initially was, what is the asymptotic behavior? What is the convergence rate at which this asymptotic behavior will be observed? Or how do the structure affect this asymptotic behavior? Like if there is associativity in the graph, then this opinion dynamics will converge faster or slower. Or if there are community structure, does that slow down opinion dynamics? These were the questions which were asked initially. But when I tried to work on this 10 years after, I saw that the questions asked are now very different. The different is, so now there is a lot of data, fine-grained data about opinion dynamics which are coming out. And now people are not much interested in the asymptotic behavior, but rather what is the transient behavior? Because the question is, when you are talking about asymptotic behavior, you are really not talking about practical terms. The transient behavior can actually cost an election. cost the president to win. So transient behavior is something which is much more perhaps practically important than an asymptotic behavior. So this is a complete shift in the question asked now also. It's not only shift in the paradigm of modeling, but also shift in the question asked now. So now what we are to ask, what is the transient behavior? Can we faithfully model the transient behavior? Match data and use data to learn this transient behavior, and not too much bother about a modeling framework which will give elegant results about the asymptotic behavior. So if we take this into consideration, and I'm taking the next question, which I thought was also coming out about multidisciplinary research. This was one question which was put forward by the organizers. So if the questions asked now are much more solid, that way much more practical, then if we have to do multidisciplinary or interdisciplinary research like on molecules or on crystals, these are very interdisciplinary research, we need a much more tightly coupled collaborations, even much more tightly coupled than what it was needed 10 years back.
Okay, maybe we can, you can wrap up and then we can start a conversation.
Yeah, yes, sure. I think I have made more than what was needed. Anyway, I will just wrap up in a very short time. So yeah, I became over serious about the thing. So the point is, what we have seen in what my experience about interdisciplinary research over the year has been that the success of deep learning has made domain people very much interested, which was hardly there. The level of interest which I see now about from a chemistry person or a biology person is much more than what I have seen perhaps 10 years back. Okay, so there are flip side that there are a lot of researchers who has begun to think deep learning as a panacea, which we have to understand. But however, a lot of researchers are really trying to understand the process and contribute in the development of the process. And I will not take the 2 slides, but in our work, we also see that there are fine contributions about domain experts who can make the system much better and much more strong, which as just a computer scientist I cannot make. Okay, so with this I will just keep it open for the things, but what for the young people, I think there will be more work on biology and chemistry. So we have to talk with people, talk with the domain people, respect their opinions, and build up the communication channel. Thank you.
Thank you. So I think it was a lot of input into the discussion. I like this last take-home message that actually biology and chemistry are really becoming much more important with graph neural networks than, you know, people in complex networks have not looked at molecules at such a level of detail and prediction kind of power. So I think that this message resonates a lot with me, because I think it's really a new avenue for new research. And of course, also the comment on opinion dynamics. I think it was not discussed much in this workshop, but it's quite interesting. And well, here with the Brexit, we had a problem of, you know, consensus emerging just before the thing and now fading down. So of course, it's a very interesting dynamics. So I think that Bruno has joined us. So Bruno, do you want to provide your perspective on this first question, which was practically what are the structure you're currently working on, and what are the exciting problems that can be faced with these structures?
Oh, thanks, Ginestra. That's that's a very interesting question. So network. So the kind of work that I'm doing, I'm very interested in how we actually learn to predict something beyond just looking at associations, right? So neural networks are essentially statistical machines. You give some input X, you want to predict Y, that's in supervised learning. And then you give many examples, and then you learn some relationship association between X and Y. So that's what it does. And in that sense, it doesn't need any fundamental understanding of the network. It does help if you have some kind of prior knowledge, so that generalization error can get reduced if you have some priors. That is also known. But generally, if you have enough data, it doesn't matter. But if you go beyond association, right? Let's say that you now want to know how this, you have trained this network in some country, or with some kind of, think of maybe opinion dynamics in some part of some social network, and now you want to apply this model in another social network, or you want to apply this model in a different country, and how would that work? Like you see, like it's no longer, if you're the statistical relationships, the associations that you saw in training are not exactly the same as you see now in tests, then you need to understand how you're going to port that knowledge into the new scenario. And that's a big open question, how we actually do that. And no matter which graph neural network we are using, none of them can do this. Zero, currently, zero, none. They, in some cases, right, they are able to port the knowledge just for kind of an accident because of the way that they work with the problem, and it kind of aligns. But it's very little understood when they wouldn't in those cases. But in majority of the cases, they just don't. And so the question then is, okay, so how do we actually use this networks or this neural networks or these methods, right? That you can actually port knowledge from one case to the other. And that to me is really a question of how do we add causality? How do we add mechanisms into our current machine learning, graph machine learning methods, right? And here is fantastic, right? Because like adding a mechanism into a neural network, you see, it's no longer just associational. So the idea of having most expressive graph neural networks, or all the work that we have done, fantastic work we have done on graph neural networks, that is absolutely not enough. We have to go into understanding what the mechanisms are for that specific type of application. And what's fascinating about this is that network science has studied a lot of this type of mechanism, right? They are not perfect. And one can argue that some of the papers are just associational papers, right? Here is like I can do some math and I produce the same plot as I saw here, but it doesn't mean that you actually learn the mechanism. It means that you are doing some association, right? But maybe maybe it's an action mechanism, right? That you are proposing there. Although recently there are more understanding of like you have to test in a causal fashion, right? But still, like maybe that's a real mechanism that they're proposing. The other thing about the mechanism is that in network science, usually things tend to be very approximated, right? Kind of a round elephant type procedure. While for machine learning, you need a bit more flexibility of molding your model to the data. But I think, so in the work that we have done for sizing variance, we were able to do both. We are able to use the theory to guide how the neural network is supposed to be designed to make that work. And so I feel that there is a lot of research on how do we get these principles that we have learned for some types of graphs in network science and apply them to learn graph representations that are able to extrapolate into another type of data set, right, that are robust to these changes. So causality will be a big problem for graph representation learning. Our group is studying this problem. It's a very interesting problem. It's difficult because now you cannot just do associations. You have to actually understand the mechanism. And here I feel that where network science can really help machine learning is providing mechanisms that we can use in our neural networks.
Okay, I don't know if you want to comment on each other statement or if you have a further comment. Otherwise, we have some next question which were already addressed somewhat in your discussion, which is what is your view on the current state of future learning-based versus model-driven approach in complex networks? Can you comment on these aspects, particularly scalability, interpretability, and accuracy? So also if you have other questions that or comment on each other statement.
Yeah, so here, so let me jump in, very kind of start this off with a kind of high level maybe comment. So I see this slightly pendular movement, right? Where we went, let's say, from model based into completely, maybe too much in some cases, data-based approaches, and now maybe going back a little bit more to a balance. So at least in wireless communications, which is a specific topic on which I've worked on graph neural network for wireless quite a bit. You know, words from 2017, 2018 were essentially, okay, let's, instead of using encoders, let's use neural networks. Instead of using detectors, let's use graph neural network or neural networks in general, etc., which they got up to some point. But now what you see is a clear trend of combining decades-old knowledge of modeling and classical solutions to problem and augmenting these with learning modules or learning parts, where the models, and specifically in communications, where we have a very clear and good physical model for how, you know, wave propagates, etc., where we have physical models that we can understand, use them as much as possible, and where things we're making assumptions that might be unrealistic, like maybe, you know, this noise we model it as Gaussian, but maybe it's not really Gaussian, or other kind of assumptions that one does, then in those cases, kind of try to use learning to bridge that gap. Right? So that kind of synergy between model and data is, at least in the terms that I think about a lot of these problems, and I think a lot of progress is made in that direction.
Yeah, so that's a very nice point of view, and I think it's a positive direction for the field. So, synthesis. Phil, do you have other comments? And of course, I think there is one main topic that I think you all covered somehow, that is the one of higher order. So feel free also to discuss more on this question of how higher order can enrich learning in graphs. And
if I can say something about this, a lot of the algorithms used today in machine learning are essentially, for instance, link prediction, right? It's predicting the links between two nodes. But the challenge is that when you try to apply this to recommended systems, it's not okay to be able to predict a link between two those, because when you make recommendations, you make multiple of those. And when we are talking about what you're predicting, you're not predicting just one link, you're predicting multiple, jointly multiple links. And the thing is that the methods, while some of them are able to kind of do this, they don't do this in a clear way. First is because a lot of the tests are actually hypergraphs rather than dyadic tasks. The second one is that the methods are really designed for pairwise predictions rather than joint. So if we want better recommender systems, then we need better ways of doing high order predictions rather than just pairwise. And I feel that the literature is missing a lot on that front.
So yeah, I can tell you what I am feeling is about some. So I've been working on this pre-training model in various ways, and so means now we can also think about various loss functions using the classical complex network structures also. That can we do? So now we are having typical reconstruction loss or typical losses, but can we, when we are trying to learn structures, so say in our problem of crystal structures, we are trying to learn the structures and how the structures behave. So this is what we are learning. So now when we are thinking of learning the structures, can we learn, for example, very simple thing, that what is the percentage of motifs which are present in the structure, and can we incorporate that in the learning algorithm so that the representation is learned using this information, this motif information. So that way there will be an interesting marriage between learning and the classical complex network structures, and this is what we are trying at the present present times too. And some of our initial results shows that gives much better results in one way. So this is one thing. Another thing is about say the fairness part. So we know, say if we have a graph and we are doing some sort of say label propagation on this graph, and if we are doing label propagation on this graph and there are some errors, means label propagation will give some errors, but this error may not be same at every portion of the graph. In some portion of the graph the error will be more, and in other portion the error will be less. So now can we connect this with some of the classical concepts of complex networks, or the classical measures of complex networks, to show that the error would be high when I'm just quoting that when in those places where the associativity is high. And in that case, if we can learn that, or if we can understand that, can we have this label propagation algorithm suitably modified so that the error is roughly similar in all parts of the graph? So this is an interesting problem which we are trying to pursue, and I feel that the old knowledge of complex networks are coming much into play when we are doing the learning algorithm, a semi-supervised learning algorithm.
Yeah, that's an interesting point of view. Yes, very. I think that this looking at probing locally the network by looking at motifs or neighborhood was a recurring theme today, and was quite interesting. The different talk, how they tackle similar questions with different tools. And yes, Phil, do you want to comment?
Yeah, sure. I'll add just one thing around one place where I think models have an exciting place for development here. And this model is actually a very simple and familiar model. It's the random walk. So a lot of the interesting work in higher order networks has in some sense, in some way, addressed some kind of question around what is an interesting walk on a data structure? What is a walk that respects some kind of graph structure or simplicial structure? And one thing that I see as an interesting gap in the literature is, I think, or not a gap exactly, but that we haven't reached consensus is, what are the useful walks on especially hypergraphs? They have a little bit less structure than simplicial complexes, and so there's lots of reasonable answers to that question. And one of the reasons that I think this is important and exciting is that walks are really the underpinning of many different kinds of algorithms, including many of our graph neural network implementations, for example, or simplicial neural network implementations have walk ideas in the layer that handles the graph or simplicial structure. I haven't personally heard, and this might reflect my own ignorance, I haven't personally heard very much about, for example, hypergraph neural networks. And I wonder if perhaps further development around the idea of walks on these kinds of structures and what kinds of features of those structures are highlighted by different kinds of walks might help further development in that direction. But I should be clear that this is very speculative, and this is also not a part of the literature that I'm extremely familiar with. And so if I'm overlooking something and someone else here is an expert on it, then please tell me, I would love to learn.
I can tell you something about K-area dependencies. Like so the standard graph neural network is based on the Weisfeller-Lehmann 1 algorithm, which is looking at communication between edges. But the K Weisfeller-Lehmann algorithm is talking about communication between K size neighborhoods, and so then the kind of the message passing is designed over this K area or K induced subgraphs. The problem with this approach, and the reason why you don't see that, I mean, we have known this for a while, right? But the reason why you don't see this very often is because it's really computationally intensive. And also the work of Maron and Lippmann uses K. It's different, but it also uses kind of K area dependencies in the graph to build their graphic permutation equivariant representation. But the reason, again, you don't see much is because it's really computationally intensive. So you can run on maybe 100 nodes, 200 nodes, but then if it's much larger than that, it's just like you can't do it. So that's really the challenge.
That's interesting. Thanks, Bruno.
Yes, so maybe we can move to the third question, which was listed here. So this is more of a kind of a personal question regarding your experience of working with a researcher across different disciplines. So the challenge to writing in papers for a diverse audience and learning from such experience. So I think that there are also in the audience some young researchers, so maybe you want to give some advice.
Yeah, so I think Niloy towards the end had an important message there, kind of keeping kind of a mind open, talking and respect. I did apply things from literature and neuroscience now in communications and kind of different things, and some of them being more technical than others. And there's, especially closer to humanities like psychology or sociology, we talk with these people, there is a clear language barrier that one has to overcome. And this essentially takes energy and time, at least in my case it did, maybe one is very used to some terms and don't even think them twice, but the other part of the communication system is not as used to that. So there's a little bit of a barrier over there. So certainly keeping the mind as open as possible and not get frustrated at the beginning, because I think it's very easy. In terms of impact itself, I believe that to have some real impact in an application domain, I wouldn't say that it's absolutely necessary. I won't be such taxative, but it helps a lot to have someone from that domain determining what are important questions to be answered, what things the community would even pay attention to, or what kind of assumptions would be completely crazy and wouldn't fly, and those kind of things that one as an outsider is very easy to miss. But once indeed those barriers are brought down, then you're on the good side, right? Because you have a high energy barrier for others to get in there, right? So it's not that you're competing with a lot of people using graph neural networks for whatever, for psychology, blah, blah, blah. Because once you overcome that barrier, then I think you're in a good position. I wouldn't say unique, but kind of a select position to try to push these interdisciplinary points. Yeah, so that's my first level. I might think a little bit and come back, but I'll leave the rest to think about.
I'd like to strongly second that last point about the importance of, if you want to reach a community, then you should really have a collaborator in that community. So here's a simple example. I'm working on a project with an animal behaviorist at the moment. And so I had some idea for a model. It was a reasonable idea. So I implemented it in my language of choice and did some experiments. Great. And if the only point is to write a paper, then the model can be in whatever language you want and make the plots and fine, done. But I was talking to this collaborator early on, and they said, well, hey, look, this is a methods paper. We'd like people to use the method. We think it's a good method. They should use it. No one is going to use it if you implement it in Julia. It has to be in R. And so even these like really simple tactical things, I see Santi smiling. Yeah, I mean, no one in the animal behavior community is going to use Julia package. It's just not a language that has reach in that community. And so really even very simple tactical things about, you want to publish some tool, how should you implement it? Where should it be? How should it be disseminated? These are very, very simple questions for which that perspective is extremely important, alongside the deep fundamental scientific questions of what's important and what's not. So get that collaborator. It really, really makes a difference.
Niloy, you also
I think I already told about this. I have broken the suspense even before when it was asked. Yeah. So I just to reiterate what I was telling, one marked difference which I am seeing in the last maybe 3-4 years, has people in the other community really think that deep learning can do something. So this is a feeling which I have got over and over again. So they are ready to talk. In say 10 years back, we have to push people, but many times people are pushing us. So they want to talk, they want to understand, and they think something good can be done. So that I would say deep learning has put into it. And this is by itself a very, very big achievement. And so on the flip side are people who think that we can do wonders, which we cannot. Okay. And so, but on the other, yeah, sure.
Sorry, yeah, I just want to say I completely agree with that. I mean, sometimes the expectations can be, completely off on the other side, and say, okay, have these 10 points, let's fit a 2 billion parameter neural network. Okay, that's not how it works, right? So, and I've seen, of course, I'm exaggerating, but I've seen that sort of attitude.
No, that is exactly what is there. Sure. But beyond that, there are a lot of serious people also who are coming out, who wants to they may not understand the entire thing, but like we would like to understand what is the input and output, even if we don't understand the process of a biology thing. They are also trying to understand what is the input and output and trying to fit things into this. And my experience in the last, when I've working on both molecules and crystals, both has chemistry people in this, and their contributions are really worth mentioning. So what I have found means what Santiago has told correctly, because chemistry traditionally has this computational chemist group. So they were computational even before, means they have their own thing. So they were trained in that way, that there is a computational thing, and now a new computation tool has come. We should interact and try to contribute as much as possible. But when it comes to psychology, or when it even comes to economics, these things becomes much more harder, perhaps still.
So I just wanted to take the opportunity to thank everyone, because I need to leave a little bit early to go teach a lecture on introductory network analysis. So I'm very excited for that. So I just wanted to thank my fellow panelists, Ginestra, for moderating, the organizers, and everyone for being here.
Thank you, Phil.
Thanks, everyone.
Yeah, to comment, like adding to the experiences, my experience, I've worked with the network scientists, I worked with a bunch of other areas, not as much with humanities. But what I found interesting, or I guess difficult, is managing what do you feel is the real contribution of what you're doing. And sometimes there are different understandings of what the contributions are supposed to be. And it's important to always talk about and understand what the other side feels is the actual contribution of something. Because sometimes what seems obvious to you, it's not at all obvious to the other side. And what's obvious to them is not obvious to you. So that's one thing. The other thing is it takes a lot of time. So you have to make sure that if you're doing a postdoc, make sure that in the beginning of your postdoc and you have 2 years to work it out. Sometimes it takes a long time to get things going, especially if you are not familiar with the area. And if you're doing your PhD, it's good that you start early. And also make sure that your goals are small and achievable in the beginning, because I have many times underestimated how much time it would take to work with other areas.
So thank you so much for this wide perspective on different interdisciplinary work with very different other fields. So we mentioned psychology, humanity, and chemistry, and then the challenge that all this can entail. So we have other question here listed. I don't know if we really want to go over all this question, but maybe it's good. So one other point that was here indicated is that what are your views on existing and newer benchmark or problems that require stakeholder for multiple disciplines? So sometimes in this discussion it seems that is a plus, is an addition, or is there something really important that cannot be addressed if one doesn't do interdisciplinary research? Can be also with mathematician, or it can be.
So it also depends upon where you want to publish. So if you want to publish in a computer science conference, many times the flavor is good enough. But if you want to publish in a domain journal, then a lot of interdisciplinary stuff is needed, perhaps. So it's also depends upon what do you want to really propose a new method, or do you want to really solve the problem? So these may not be the same thing, and how we interact there depends, I think.
But there are real problems that you think they are, important for the field. That you, when you work with a collaboration, are you also solving some problems that are new, that emerge from this collaboration, that are new in the sense that are new theoretically, or like...
I mean, so my view is, I mean, sometimes these collaborations end up motivating, let's say, a new, more formal problem. And that formal problem one can try to tackle at whatever level of abstraction one wants. But then, like, the actual practical problem, it usually requires, cutting corners and making something that is specific to that application, or at least in my experience, to that application, to that data set and stuff like that. So things don't end up being as clean as in the theoretical abstraction that what has been motivated by that problem. So sometimes then a new problem itself maybe end up being decoupled into, this is a cool theoretical problem that has been inspired by that. And then this is the actual thing that tries to solve that is a little bit more messy and dirty than the other one. So yeah, so it can still solve new, let's say, methodological problems, but maybe that's not just the key to open that door. So,
yeah, exactly. I think that's what I was trying to say. Giving a new method and solving a problem may not be the same thing. Yeah.
Yeah, I agree.
I agree with this view, and also I found myself oftentimes challenging some of the notions, because machine learning, in a way, it's broad and narrow. Like usually the problems are very narrowly defined as simple tasks, and they are not that simple in reality. They tend to become over time oversimplified. And whenever you go back to the original problem and talk to experts, they say, no, this is too simple. It has to be like this. And you're like, well, like this, there are no techniques. We don't know how to solve. And that really has helped a lot the field in general.
Absolutely.
Absolutely. So let me just conclude with the last question. So what are your suggestions for young researchers on ways to identify problems that require multidisciplinary approach, or or involving complex graph? What is your way of your suggestion or way of working with this? So how do you build team? How do you find collaborator? If you identify some challenging interdisciplinary problems, so how is it? Do you navigate?
So just one point to maybe get that one started is, so I don't know if I would just think of what is the next interdisciplinary problem just like that, right? But what I'm quite open to discussions in general. As someone comes to give a talk here at Rice, I just talk with them and this and that, and then I'm a big fan of kind of some of these things. If they're gonna fail, kind of making them fail very fast, right? So kind of the first hour of a meeting with someone, an hour you talk with anyone. It doesn't matter what they do. biology, chemistry, whatever. You just talk for an hour with these people. And most of them, 90%, don't go over that first meeting just because it's not a good fit or this or that. And then they would naturally filter quite fast until hopefully some nice ideas with some collaborators end up surviving this process. So maybe just start a lot of potential seeds and make them fail fast and just keep the good ones. That's maybe a possibility, but maybe this is not the method of everyone. That kind of works for me.
So for the young people, I can say one thing, that you should listen to a lot of talks. That is one thing. And with this COVID, it has actually opened up a huge possibility that you can, previously only you used to listen to talks which came to your university or people, but now you have a huge possibility, and everybody should take advantage of that and listen. That is, I think, very, very important. Then other things will follow. Once you will develop a knack, other things will follow.
Just it's slightly different than the question. My suggestion that I give to all my students also is whenever you learn something, go back to the original paper that wrote about that thing. Don't follow books or what other people wrote, because you miss a lot of what the original author wanted to say, even to the point. So if you have not read papers from the 70s or the 60s, something is not quite right, because a lot of what you are learning now happened at that time. And at that time, they had many interesting questions that they asked. And we have distilled those ideas to something so simple that we miss the kind of the more complex situation that they were starting to describe. And there are many other ideas that you can follow from those seeds that those folks planted, because they are not describing one idea, they're describing many. And then we distill to a simple method. But if you read those, so even I would suggest even go to books from the 30s and the 20s, when say learn maximum likelihood. Go read Fisher's definition in books of maximum likelihood to understand the idea he had and how that evolved in what we have today and what has been missing from the way that he had defined it. So my suggestion is always, whatever area you study, go back to the papers, even if it's very old, and read those. It's very important that you understand that. That's my suggestion I give to all the students.
Okay, thank you so much. I think we had 3 answers which reflected 3 different aspects of things that need to be pursued in any case. And I think, yes, I think we can probably conclude here the discussion. I think we are exactly on time. I think we have only 2 minutes for the end of this session. So I would like to thank everybody. Welcome, and thank you for this panel. It has been really a pleasure to host you here.
Thank you.
Thank you, Niloy. Thank you, Santiago. Thank you, Ginestra, and everybody.
Thanks, everyone. Yeah, take care. Nice to see you, Bruno, again. Thanks, everyone. Take care.
Bye.